And we are back with more CLEP calculus sample practice exam questions from the internet from here. Link should also be in the description. And we are going to pick up where we left off, which was, we just did 44, 45 we've done before. Here we are at 46. So g is a continuous function such that the definite integral from 0 to 2 is 7. The definite integral from 0 to 3 is 5. And the definite integral from 1 to 3 is -1. So from all that, what is the definite integral of the function from 1 to 2? So for this, let's just draw out a little picture. 0, 1, 2, and 3. So it's telling us that from 0 to 2 is 7. From 0 to 3 is 5. And from 1 to 3 is -1. So what can we glean from this? Well, the difference between 7 and 5, if this is 7 and this is 5, what does this have to be? What can we add to the 7 to get to the 5? And that would have to be a -2. And what would this have to be? What could we add to the -1 to get to 5? And that would have to be 6. So again, what's that middle part going to be? And we could find that in any number of ways. If this is 6 and this is 7, what's that going to be? If this is -1 and this is -2, what's that going to be? Or you could do the whole boat. You could have a 5 and a -2 and a 6. But any way you slice it, we know that bit in between is going to be 1. 1 and 6 make 7. 1 and -2 make -1. 1 and 6 and -2 makes 7 minus 2 makes 5. So it's just piecewise. We don't even have to draw the graph. We don't know what the graph looks like, but we know that the area in this distance, and this distance, and this distance are the values that they give us, and that piecewise they have to add up to the wholes. So from 1 to 2, it is a value of 1. And that is the answer. Okay. Number 47. Let f be a differentiable function with a domain from 0 to infinity. And a reminder, the domain means the independent variable. We're talking about the x. So we're talking about x values from 0 to infinity. And the range, which means the possible y values, are going from -infinity to infinity. So we're talking about positive x values, and the y values are expected to be negative and positive with no limit there. Okay, so such that f of 2 equals 3, which means that at x equals 2, the y value is 3. And the derivative at 2, or the slope at x equals 2 equals 1. And it says the function is increasing. So we know that the derivative for all x is positive, is greater than 0. And the graph of f is concave down for all x. So concave down means the second derivative is less than 0. It means even though the slope is always positive, it is getting smaller, is becoming a lesser positive number as you go along. So let's try to envision what this looks like, first of all. So we know that this point exists of x equals 2 equals a y of 3. So that is a point on the graph. And at that same value, the slope is 1. So it's kind of looks like that going through there. And the graph is always increasing. It's always a positive slope, but it's concave down, so it's getting smaller as it goes. So it's kind of starts higher than 1 and then crosses 1 at that point 2, 3. And then as it keeps going, it's still positive, but getting smaller as it goes, somewhere up there, you know, drawing not necessarily to scale, but that gives you some idea of what we're looking at there. So that's the picture that it's giving us. And then what is the real question? It says we have another function g, which is the inverse of f to the -1. That just means the inverse. What does the inverse means? It means we are swapping the x's and the y's. So we're taking this and we're flipping it over this way, right? So let's actually draw that so we don't have to just picture it in our head. Now that kind of curves up that way. So when we mirror it out, it's going to kind of curve up that way. And we had a point 2, 3. And so that point is now going to be 3, 2. Again, not really to scale, but we have a point 3, 2 where that slope, because we mirrored it this way, the slope at that point is still going to be the slope of 1. The slope of 1 is parallel to the direction that we're mirroring it. So that doesn't change. That's actually still a slope of 1 right there. But instead of going up this way, it's going up this way. And this is the graph that it's now asking us questions about. So we have to, you know, have it pictured in your head, or drawing it out. That's easier. Or draw this out and imagine it flipped over in your head. You know, whatever gets you through it the quickest. So on which of the intervals is the derivative or the slope less than 1? So we already said that it equals 1, g of x equals 3, right? Because it was the y of 3 before, but we mirrored those, so it's the x value of 3 where the slope is 1. So where is the slope less than 1? Well, we can see it's going to be over here, right? Because it's increasing here, and over here it was less. You know, on the original graph, it was decreasing as we went this way, but because we flipped it over, now it's increasing as we go this way. So it's less than 1 in this interval, ending at 3 and going that way. And remember, I drew this as if it ended at 0, but because it told us the range is negative infinity to infinity, it's actually more likely that it is more like this. That presumably doesn't even have a point where it crosses the y-axis. It's kind of probably approaching it asymptotically and never reaching it that way. It can go down into infinity. And same with this one. It's probably, the intent is probably actually that it's continuing on that way, asymptotically approaching the x-axis but never touching it. So we're actually talking in terms of from 3 over that way, over this way is the negative infinity, right? So, and we can tell from the options, there's only one where the upper bound is the 3. It doesn't, the slope less than 1, it doesn't start at 0, it doesn't start at 2, it doesn't start at 3, it stops at 3. So D is the best option, and D is the answer, and then obviously not E, because that means the whole thing. But it's not. It's D. It's everything, and then stopping at 3, because after 3, the slope is greater than 1 as it goes up. So that's, a few steps to go through to get to that one. You kind of have to work out what it's saying and then work out what that looks like flopped over. But that's how we do that one. So, and then, 48 we've done before, 49 we've done before. And I think we have a few more pages. 50 we've seen before, 51, 52, 53, 54, 55. All seen before. 56, 57, 58, 59. Remember that one? That was fun. 60, all seen before. 61, 62, 63, 64, 65. Done all those before. 66. Okay, 67. Here's one that's new. And I did kind of whiff past it, but we did cross over into the calculator's allowed portion. So let me go fetch the calculator, because as you can see by the answers being in decimals, we are definitely going to be using the calculator on this one. So let's see. Let's go. We gotta go to the Y. So it is giving us. So it's talking about the function is the definite integral of 1 to x of sine squared of t dt, for x being somewhere between 1 and 12. And this is just in terms of, what are we looking for and what do we have. Because the graph goes in terms of x and y, we are going to put in the sine of the square root of x. But that x is not the same as that x. You could, substitute the x for the t and substitute like n for the x as what we are looking for, rather than the x in terms of the graph, in your head. So let's see what that looks like. And let me adjust the zoom so we can see it a little bit better. Let's do let's do the zoom integer. And then let's do the zoom in. And let me change the tick marks. And you can almost, let me adjust the window a little more. Let me add to, all right, now we can see it a little bit better. It goes up, and then it crosses, and it goes down. And what we're being asked is we're doing a definite integral from 1 to somewhere. And what is that somewhere for that integral to be the highest? You know, what if we start at 1, where do we stop to get the highest value? And of course, we stop where it crosses the x-axis, where it hits 0, because beyond that it goes negative, and you start subtracting from the area. You know, so what we're really asking is, where does the sign of the square root of t, or x, you know, cross the x-axis there? And we can trace over to there. You can obviously use the math functions to find it exactly. But if we trace our way over there, we can see that it's going to be somewhere between 9.75 and 10, right? So 9.8 is a pretty good guess. But if we go to, let's see, the calc menu, and we ask it for the intersect no, not the intersect. Sorry, we only have one. The zero meaning the root, meaning where the function is equal to 0. And it says left bound, so we know it's somewhere greater than 975 and somewhere less than 10. And it's somewhere in there, and it grinds, and it tells us 9.8696, which rounds to 867, which is, of course, that. But we already knew that because it was definitely between 9.5 and 10, and not any of those other values. So that's what that one is. Okay, moving on. 68. An object on the moon is launched upwards with an initial velocity of 25 feet per second. So we have a velocity at time 0 where the first derivative is the velocity. If the normal graph, if the normal function is position, then the first derivative by distance over time is the velocity. So the velocity at time 0, your initial velocity, is 25, right? From an initial height of 40 feet above the ground. So a height at time 0, meaning the regular function, the position function, right, or the height function in this case. So just the normal function at time 0 equals 40. And the acceleration of the object is negative 5.3 feet per second. And so as I mentioned or neglected to mention in the review video, when we're talking about velocity and acceleration and so forth, a negative value just means the opposite direction. So in this case, a positive value is going up and a negative value is going down. So the acceleration is negative 5.3 feet per second, just meaning it's 5.3 in the downward direction. And the acceleration is constant. So the second derivative for all values of t is negative 5.3. Again, the regular function is the height, and then the derivative per time is the velocity, meaning the position per time, or speed, feet per second. If the height in feet, and you take the derivative of time, getting feet per second, that's the velocity. And then how is the velocity changing over time? That gives you the second derivative, feet per second, or feet per second squared. So that's how the physics and the calculus work together in terms of what the first derivative and the second derivative represent when we're talking about this. So how many seconds after the launch does the object hit the ground, meaning at what t value is that height equal to 0? So we have to work out what the whole equation actually is based on these known values that were given. So we know the acceleration is just plain old minus 5.3, and that's the second derivative. So we can integrate that. We want to find out what the first derivative is based on that. And when you have just a constant value and you integrate, that means you're going to move the variable in, because if you take that and you take the derivative, integer of 1 moves down, 1 minus 1 is 0, and it goes away. So when you take the integral, you bring it back, so it's a t instead of an x, because we're doing it in terms of t. Works the same way, we're just talking time instead of an x value. And then that would be plus c, the constant. But we also know that at t equals 0, that first derivative is 25. So if t is 0 here, and then you're just left with the c, it has to equal 25. So that c must actually be 25 plus 25, like that. First derivative. And then we do the same thing again, because we want to try to find that original height equation. So we take the integral again, and again, just reverse power rule, because this is t to the first. When we take the integral, it has to be t squared, because to get from here to here, we subtract 1. 2 minus 1 becomes the 1. So we have a 2 there, and then as we go from here to here, we would be moving the 2 down into the front. So 5.3 has to be whatever this is times 2, right? So we're just going to write 5.3 over 2, right? As you move the 2 down, it cancels out the 2 on the bottom and leaves you with the 5.3. And then with the 25, we're just adding back a t. And then we still have that c, that constant. But again, because we were given that initial value at t equals 0, the whole thing equals 40. So when you fill in 0 for these, they go away, but whatever you're left with has to equal 40. So that position is negative 5.3 divided by 2 times t squared plus 25t plus 40. Okay. And that is not necessarily a nice equation to deal with, but fortunately we are in that calculator section. So again, if you remember from further back, solving a quadratic equation that if the for 0 equals ax squared plus bx plus c, that the x values are equal to negative b plus or minus the square root of b squared minus 4ac over 2a. You could do it that way. But because we are dealing with a graphing calculator, we can actually just graph the whole thing and see where it hits that x-axis. So we're going to put in negative 5.3 divided by 2 times, and again we have t for time and the height, but because we're putting it into the calculator, we're going to translate that back into x, standing in for the time, and the y standing in for the height. So plus 25x plus 40. And we are going to adjust the window. We know we're going to start at a time of 0. So we're going to do -1 to make sure we can see things. And the final value, it's probably going to hit the ground, might be, let's just make sure, in case it's more than 10, let's have our window a little bit beyond that. And the ground is 0, so let's make that a little closer to 0, and it's going to go, well, started 40 feet in the air, so it's going to go pretty high in the air. Let's just say 100, and graph that and see what it looks like. And there we go. So here you're starting at 40, you throw it upwards, and it goes over this period of time. It goes all the way up to here. That's where gravity drags it to a stop and starts to bring it back down. And then as it gets over to this time value, this axis is time, that's when it finally hits the ground and reaches the 0. So we can trace over to there, and we can see it's going to be, somewhere between 10.6 and 10.8, something like that. And we can go to the calc menu, we can find the 0, and we can say it's going to be between there, and grind, and it'll tell us at 10.82. But it actually, well, give your answer to the nearest integer. So we already definitely knew it was somewhere between 10.5 and 11, which rounds up to 11 in any event. So we didn't even have to necessarily ask the calculator for the intercept, just by running the trace and examining it on both sides of the intercept. We could easily conclude to 0 decimal places that it was going to be 11. Right? Okay. Moving on to number 69. So the function has a derivative, which is x squared minus 4x over x minus 2 squared. And on which of the intervals of the graph is f decreasing, meaning where is the derivative negative, and where is it concave up, meaning where is the slope increasing. So where is the derivative negative but increasing? Right, because concave up is where, concave up going this way is where the slope is increasing as you go along, but we want it to be negative because the graph, the actual original graph, is decreasing, meaning the slope is negative. So it's going down but increasing, getting less downwards because the slope is negative but becoming less negative as you increase. So let's figure out what we can do with this. The derivative is x squared minus 4x over x minus 2 squared. And we can kind of make an educated guess here. In terms of the zeros of this are going to be, where does this whole thing equal 0? That's obviously going to be at 0 because 0 minus 0, but then it's also going to do something at 4 because 4 squared minus 4 times 4 is still 0. So the two zeros of this are going to be at 0 and 4. So there's something going on at 0 and there's something going on at 4. Because this is the calculator's allowed portion, it's just far easier to throw it on the graph and see what's going on. Minus 2 squared and so, okay, we can, as you can figure, because it's divided by an x minus 2, it does not have a value at 2. Well, if I had this, it's set so it was evenly spaced x values, you would see at 2 it does not exist because it's going down asymptotically to and back from negative infinity at 2. And then right here, here's that 4 we were talking about, and you can see it's crossing the x-axis. If I say trace and I say 4, y equals 0, and you can kind of see that as you trace back and forth, that 4 is in between where it flops from negative to positive, or you could, you can punch in the 4, or you could adjust the window so that the trace gives you nicer values, whatever. It's definitely 4 there. So remember what we were saying, which of the intervals is the graph decreasing, meaning where is the slope negative, so we can tell it's negative from here to here. And what is that over there? We think it's 0, right? Looks like it should be 0. It is 0, 0. So it is negative between 0 and 4. So one of the conditions is met between 0 and 4. The graph is decreasing because the slope is negative. And then it's asking where is it concave up? Where is the slope increasing? Where is the slope getting more as you go that way? And obviously, as you approach x equals 2, shooting down to negative infinity, that is decreasing. But as you go past x equals 2 and come back up, it is increasing. and then there's a horizontal asymptote at y equals 1, because if you go further along, it gets closer and closer to 1, but never quite gets there. So the slope is increasing by ever so slight amount forever, never quite getting to 1, but always getting closer and closer to 1. So where is the slope increasing? It is increasing from 2 to infinity, right? So one condition is true from 0 to 4. The other condition is true from 2 to infinity. That means where are both conditions true? Where do these overlap? It is from 2 to 4. So the answer is C. Okay. All right, number 70, last one for this set of questions. F is a continuous function such that it is greater or equal to 0 between x equals 0 and x equals 2. So just we're dealing with positive values from 0 to 2. But then x is less than or equal to 0 from 2 to 5. So from 0 to 2, it's positive. I'm going to draw a little graph here. 0, 2, and 5. And so from 0 to 2, it's some kind of positive value, but then obviously it switches from positive to negative at 2, and then stays negative at least out to 5. So I drew a straight line. We don't know for sure if it's a straight line. It could be curved. The shape doesn't really matter because what it tells us doesn't involve the shape. The rest of what it tells us is that integral from 0 to 2 in that positive region is 6. So the area in here is 6. And then the integral from 2 to 5, meaning all that negative region where it's negative, the area is -8. And remember, the negative just refers to being below the x-axis, because those are negative values. So that's the -8. So what is the value, the ultimate question, what is the value of the integral from 0 to 5? So 0 to 5, we're talking about the whole thing. What is the integral of the whole thing of f of x? So just the normal graph, then plus the absolute value of f of x. That's those two vertical bars. Two vertical bars around something means the absolute value. The absolute value means we're just chopping off the sign. So all negatives become positives, and all positives just stay positive. So, and we're adding these together, so it is the area of the whole thing, and then the whole thing again, but with negatives turned positive. So we have the whole thing is 6 plus the -8, and then the whole thing again is 6, and then instead of a -8, it's going to be +8 because we're taking that absolute value. So 6 plus -8 plus 6 plus 8 is the ultimate answer, and -8 and +8 cancel each other out. 6 plus 6 is 12, and that is the answer. And we have reached the end of that particular one and the end of the video.